In earlier class we have talked about the potential energy, how we calculate the potential energy of a system of charge. If there are n particles in a system, then we have to make pair which is equal to the n into n minus 1 by 2. Now we have seen that we have solved some problem related to potential energy. Again, some new problems we will see here. For example, here a problem is given, that is Q1 and Q2 are fixed. Q3 can move and release from rest. Find the speed of the Q3 as it reaches O. The situation is shown in the figure. Here Q1 charge is Q1 and Q2 are placed on the x-axis, that is Q1 is at 3 meter from origin. It means that its x coordinate is 3 meter and y coordinate is 0. Similarly, the Qt is at minus 3 meter from the origin, or 3 meter from negative sign for it to show that it is on the left side of origin. So its coordinate is minus 3 comma 0, and similarly Q3 charge is placed at a distance of 4 meter on the y-axis, and we have to calculate from rest. Find the speed of the Q3 at as it reaches O. We have to find they are at rest and Q3 is released. Then we have to find the velocity of Q3 when it reaches O. The value of Q1 and Q2 is given 2 microcoulomb and Q3 is minus 4 microcoulomb. Also the mass of Q3 is given 1 gram. To solve a problem, let's consider. Let V be the speed of the particle at O. From conservation of mechanical energy, Ui plus Ki, that is initial potential energy plus kinetic energy of the system, equals to final potential energy plus kinetic energy of the system. So we have initial potential energy 1 by 4 pi epsilon naught Q1 Q2 divided by R12 initial plus Q1 Q3 by R13I initial plus Q2 Q3 beta R23. That is, this represents distance, initial distance between the charged particles, plus 0 because initially Q3 is at rest, so potential energy will be 0. Kinetic energy will be 0, and equals to 1 by 4 pi final potential energy 1 by 4 pi epsilon naught Q1 Q2 R12 F. F represent the final distance between Q1 and Q2, or charge 1 and 2. Similarly, Q plus Q1 Q3 by R13 F plus Q2 Q3 by R2 F, and plus 1 by 2 mv square. We are considering that the velocity of charge 3 at O is V. So this is the kinetic energy, final kinetic energy of the particle. Here R12 initial equals to R21F final, because distance between 1 and 2 is not changing, only distance between 1 and 3 and 2 and 3 is changing. And R13 initial will be under root 3 square plus 4 square from the diagram shown, equal to 5 meter, and R23 initial equal to under root 3 square plus 4 square equals to 5, and R13 final will be 3 meter and R2F final will be 3 meter. So using all the given value, we have 1 by 2 mv square equal to 1 by 4 pi epsilon naught, taking because this term will be cancelled out, this term and this term will be cancelled out, because there is no this distance and this distance are equal, so this distance will cancel out, only we are left with this and this term. So 1 by 4 pi epsilon naught Q1 Q3 by R13 initial minus Q1 Q3 by R13 final plus Q2 Q3 by R23 initial minus Q2 Q3 by R23 final. And now using all the given value, 9 into 10 to the power 9 and another value, finally we comes out to be here and solving uh, we have 9 into 10 to the power minus 3 into 32 by 15. So v square will be equal to 2 into 9 into 10 to the power minus 3 into 32 by 15 divided by 1 into 10 to the power minus 3, because mass is given 1 gram, so changing it into kilogram, and finally we get v equals to 6.2 meter per second as a result. Next question. Here the figure, in the figure we see that two charges are placed at a distance L. System is released from rest. Find the speed of the particle when the separation is reduced to L by 2. Given mode of Q equal to 4 into 10 to the power minus 5 coulomb. That is value of charge. Magnitude of charge is given. And M equal to 5 gram and L equal to 1 meter. Initially it is given distance is L equal to 1 meter. Here again we can use the conservation of mechanical energy, considering these two particles as a system. So we have conservation of mechanical energy. Initial potential energy plus initial kinetic energy equals to initial final potential energy plus final kinetic energy. Now initial potential energy is 1 by 4 pi epsilon naught q into minus q by L, because given it is one is a positive charge and another is negative charge, and distance is L initially, and initially there is no motion because it was kept in a rest initially and then released, the plus 0 and equals to finally when it distance becomes L by 2, so 1 by 4 pi epsilon naught q into minus q and divided by L by 2 plus 2 into 1 by 2 mv square, because both will move with same velocity, because both same electrical force is acting, so they will get same velocity. So 2 into 1 by 2 mv square. Now this implies mv square equal to q square by 4 pi epsilon naught minus 1 by L or minus 2 by L equals to mode of q square by 4 pi epsilon naught 2 by L minus 1 equals to mode of q square 4 pi epsilon naught into 1 by L. Hence v square will be equal to q square by 4 pi epsilon naught m into L, and using all given value finally we get v equals to 12 into 5 into 2 by root 5, or 24 into root 5, or 24 into root 5 is 2.236 equal to 53.664, equivalent to 54 meter per second. Answer. Now we have seen that the problem related to the conservation of mechanical energy in case of electrostatics, or in terms of potential energy and electrical potential energy and kinetic energy. Now let's see, our next topic is electric potential. So what is electric potential? First let we define it. So it is defined as the amount of work done required in carrying unit positive charge, test charge. Unit positive charge means test charge, slowly from infinity to a certain point in an electric field or vice versa. If Q be the point source charge and Q be the point test charge separated by a distance r, then by the definition of potential energy we have work done by external agent to bring the charge from infinity to r, that is work done in taking charge q from to infinity to the point pr, equals to, hence we have u equal to 1 by 4 pi epsilon naught q into q by r, and this is equal to the work done by external agent infinity to r means that work done in the taking charge q from infinity to the point charge point pr, or hence work done in taking unit positive charge from infinity to the point pr will be equals to work done external infinity to r by q. That is we have divided it with charge q, so this will give the unit work done by using unitary method. So by definition, this work done is work done on unit positive charge is equal to the potential of the system. So by definition, potential V equals to, so by definition, potential V equals to in external work done in to bring infinity to r by q, del w external in infinity to r divided by q, where q is the test charge. So we have V equals to, by the definition, 1 by 4 pi epsilon naught q by r. So if we see, if there is a charge q and we have to calculate the potential at a distance, potential at a point p who is at a distance r from the charge q, then potential at this point p will be given by this formula V equal to 1 by 4 pi epsilon naught q by r. Now unit, since V equal to W by Q from the definition, so the unit of work is joule and unit of Q is coulomb, so joule per coulomb is its unit. In MKSQ system, and joule per coulomb is called volt, and dimensionally V equal to dimension of W by dimension of Q. Dimension of W, that is work, is ml2 t minus 2 divided by dimension of Q, ml2 t minus 2 q minus 1. Note, in the above formula for potential, Q is placed with sign. Next, electric potential due to a system of charge. If there is a system of many particles, many charged particles, and we have to find the potential at a given point, then we should find the potential individually and add up it to get the total potential. So net potential at point P will be potential due to all charge at point P. So potential at point P due to all charge is equals to Vp, or Vp equals to 1 by 4 pi epsilon naught q by r1 plus 1 by 4 pi epsilon naught q2 by r2 plus dash 1 by 4 pi epsilon naught qn by rn, where n represents the nth charge. Or in generalized form, we can write Vp equals to, that is potential at point P equals to 1 by 4 pi epsilon. We can only write V also. This P is this P symbol is used to represent the point P. There is no need to write everywhere it. We also can write only V to represent total potential at P, but formula will be same. Vp equal to 1 by 4 pi epsilon naught sigma I equals to n qi by ri. This is the summation over the ith particle. Our next topic is potential due to continuous distribution of charge. So we can find the potential V equal to integration dV. We have to take elementary charge, and then we have to find the potential at a given point using the formula for a single point charge, and then integrate it in the proper limit. We will get the potential due to continuous charge. So V equal to integration dV equal to 1 by 4 pi epsilon naught integration dq by r, where dq is the elemental charge. For example, find potential at point electric potential or potential, because we are here discussing electrostatic. So whenever we tell potential, it means electric potential. Find potential at point P due to charge as shown. Q1 equals to minus 4 microcoulomb, Q1 equals to 4 minus 4 coulomb, and R1 equal to 2 meter. This is shown in figure. And second, it is a system of 3 charge. Q1 equal to 4 coulomb, Q2 equal to minus 5 coulomb, Q3 equal to 2 coulomb, R1 equal to 4 meter, R2 equal to 6 meter, R3 equal to 3 meter. It is shown here. And third, Q1 equals to, given this value, Q1 equals to 2 coulomb, Q2 equal to minus 5 coulomb, Q3 equal to 6 coulomb, R1 given 1 meter, R2 2 meter, and R3 3 meter. That we have to find similar, because it is a vector, it is a scalar quantity. We find it visually and add up. So in one, Vp will be 1 by 4 pi epsilon naught Q by R1, or 9 into, because this value is 9 into 10 to the power 9, and Q1 is given minus 4 in by 2, or minus 18 to 10 to the power 9 volt. Similarly for second, Vp will be 1 by 4 pi epsilon, taking common from all terms, Q1 by R1 plus Q2 by R2 plus Q3 by R3, under bracket 4 by 4 plus minus 5 by 6 plus 2 by 3, volt, unit is volt. And solving this, we get 9 into 5 by 6 in 10 to the power 9 volt. Again for 3, Vp will be 1 by 4 pi epsilon Q by R1 plus Q2 by R2 plus Q3 by R3, and equals to 9 into 10 to the power 9, 2 by 1 plus minus 5 by 2 plus 6 by 1. And solving this, we will get the desired result. Now again we have to find the potential at a point O. The situation is shown in the figure. How can we solve? We have to find first, because this distance is given, charge is given. So now we have to find the potential at O. So we must know this distance and this distance, and this distance. Because it is a square, only knowing one, we can use right angle triangle method to find this distance, and then half of this will be this distance, and this all distance will be equal to each other. Okay, this distance will be equal, so we can easily find the potential. Same case is here. Here also it is a square, so we can solve easily. Again here it is a not equilateral, equilateral triangle, so we can find this value, because charge is placed, so we can find this value, which is equal to, and value of A is given √3 here value of A is given, then we have to find. So solution for 1, here potential will be 0, because here we see this is positive, and all have same distance, and the charge is equal, so this will add up, and this is negative, so this 2 will also add up, and now when we add algebraically, that this will give us to 0. So potential will be 0 at in the first case. We all charge have same magnitude, and 2 are negative and other 2 are positives. Also all charges are at same distance from O, so it will be 0. Now in this case also will be 0, because all have same distance from the O, and there are 2 positive charge and 2 are negative charge of equal magnitude. So in this case also, in second case also will be 0. So Vv equal to 0 for the same reason. And the third, V0 will be 1 by 4 pi epsilon naught plus 4 by √3 by √3. Because this distance is equals to A by √3, and A is given √3, so this will be A by √3, so √3 by √3, and this one will cancel, this potential due to this will cancel this, and only we are left with this potential. So we have written here in this case, because potential due to this charge will be negative, and potential due to this charge will be positive because both have same magnitude of charge but in opposite sign. So this will add up to give this will cancel each other and only we are left with this charge, so will be potential as given in this formula. Next we have to find the potential at P. It is given a linear charged rod of length L with linear charge density lambda, and we have to find a potential at P as shown in the figure. So what we have to do here, first we find the potential due to elemental charge and then integrate it to the proper limit. So dq will be lambda dx if we consider at a distance x this elemental charge from the origin. So element of length dx at a distance x from the origin. So dq will be lambda dx. Now do dvp, that is elementary potential at point P, will be, because we have to find this distance, so it will be 1 by 4 pi epsilon naught dq by r, or vp equal to integration dvp 1 by 4 pi epsilon naught. Integration will be from a to a plus l, dq by r. So a to a plus l dq by r, or 1 by 4 pi epsilon naught a to a plus l lambda dx. Now r will be under root x square plus b square. So under root x square plus b square lambda by 4 pi epsilon naught, and integration of this will be equal to log x, log under braces x plus under root b square plus x square from a to a plus limit from a to a plus l. So putting the limit value we will get lambda by 4 pi epsilon naught log. We have to put because x is variable, so we have to put the in the limit value of x as a plus l and a. So first we have log a plus l under root b square plus a plus l to the whole square divided by a plus a and under root b square plus a square. Now case 1, when b equals to 0, that is point is at O, then what will happen? We have to see. Then vp will be lambda by 4 pi epsilon log b will be here 0, so a plus l plus a plus l divided by 2a. So at this point potential will be given by this formula, or again solving it, vp will be lambda by 4 pi epsilon log 1 plus l by a. Again next sub case, if a is very greater than l, that is point p is at a large distance, then l by a very less than 1 and log 1 plus l by a equivalent to l by a, because we have formula log 1 plus z equivalent to z when if z is very less than 1, then this formula is used. And so we have this log 1 plus l by a equal to l by a. So our formula will be vp equal to lambda by epsilon naught l by a on 1 by 4 pi epsilon naught, because lambda into l equal to q by a. That is the rod behaves as a point charge when the point is very large distance, at a large distance. Case 2, when a equal to 0, then vp will be lambda by 4 pi epsilon log, putting a equal to 0, l plus under root b square plus l square divided by b, or vp equals to lambda by 4 epsilon naught log under bracket l by b plus under root 1 plus b square by l square by b square. Sub case if b is very greater than l by b equivalent very less than 1, hence 1 plus l square by b square equivalent to 1. Hence Vp will be, so of case if B is very greater than L, then L by B will be very less than 1, and hence 1 plus L square by B square equivalent to 1. Hence potential at point P, that is Vp, will be lambda by 4 pi epsilon or log 1 plus L by B. Equivalent to lambda by 4 pi epsilon naught L by B, or equals to 1 by 4 pi epsilon naught Q by B, which is again as a due to a point charge.